Another type of graph of motion that we can examine is a velocity versus time graph. In this case, we look at how the velocity changes rather than how the object's position changes. Let's take a look at the things that we're going to focus on in this video, including how the axes tell us what's going on, how slope can be calculated, and then how we can use all this information together to sketch a v versus t graph when we're given an x versus t graph. So here's an example of a velocity versus time graph. We want to be able to understand what this graph is trying to show us, and the units on the axes will really give us the main clue. Of course, slope is rise over run, and as we take a look at the units on the rise axis, we see that that's meters per second. And then along the run axis, that is seconds. And so our slope will not be meters per second as it was with the other graphs. It will be meters per second per second. And so this introduces us to the idea of acceleration. Okay, acceleration will have units of meters per second, and that slope, measured in meters per second, tells us how quickly the velocity changes. So a high value of acceleration, it could mean a very large change in velocity, but it could also mean a moderate change in velocity, but in a very short amount of time. Let's take a look at a section of this graph and just try to understand what the slope tells us. So this initial section from 0 to 20 seconds, we can tell that the object's speed begins at 50 meters per second and increases gradually to 100 meters per second during those 20 seconds. So what we can say here is that the speed is increasing, and this is the way that most people think about the word acceleration. But in our class, we will see that there are a number of different ways that the word acceleration will be used. See that in just a second. But let's look at the middle section from 20 to 30 seconds. In this section, the slope is 0, it's a horizontal line, and that corresponds to this object's velocity remaining the same, a constant 100 meters per second. There is no acceleration, there is no slope. During the last interval, the object's speed changes from 100 all the way down to 0. It's brought to a stop. This is something we would probably call deceleration in our everyday language. In our class, we will also call it negative acceleration, and that corresponds to the negative slope of this portion of the graph. So let's take a look at actual calculations and sort of see how this all comes together. So if we wanted to know the value of acceleration during that first interval, we would choose 2 points on that section. Doesn't matter which 2 points. All the way throughout this interval from 0 to 20 seconds, the acceleration can be found by taking 50 meters per second as the rise, and then 20 seconds as the run. So 50 over 20 is 2.5. And then our units, again, the seconds do not cancel out. This is meters per second on the top, and then it's also per second on the bottom. So meters per second per second. That middle section, we don't even need to calculate. Hopefully we know that the slope of a horizontal line is 0. But in this case, that 0 slope doesn't mean that the object isn't moving. It means that the object has a constant velocity. And so in that case, we would say that there's no acceleration or that the acceleration is 0. In the last section, we can see that the graph slopes downwards. This does not mean that the object moves backwards. What it means is that the object's velocity is slowing down, is decreasing. And so there's a change of 100 meters per second from 100 down to 0, and that requires 10 seconds. So our slope is -10, our acceleration is -10 meters per second per second. Let's take a look at how we might change these graphs of position versus time that we've seen in the past. See how we can build a graph of velocity versus time from that information. So let's take a look at the red line first, the line that's labeled A. And we can see that on the position versus time graph, that is a straight sloped line. That is an indication of constant speed, constantly changing something's position with time, very consistent motion. On our velocity versus time graph, that's going to show up as a horizontal line. But because that slope from the top graph is negative, the velocity on the bottom graph is negative. This object is moving backward. If we take a look at the B line, the green one, here we have a positive slope when we look at how position changes. That's going to be a positive value of velocity on the bottom graph. So what we want to see is that the slope of the top graph tells us the value on the bottom graph. Okay, well, what if the slope is changing, like it is in graph C? So graph C has a slope that is initially 0, it's very flat, and then gradually the slope gets greater and greater. Remember, slope on the top graph tells us how fast the object is going. So this object keeps on going faster and faster. It's speeding up. This would look like a diagonal straight line on the velocity graph. The object's velocity is increasing after starting at 0 speed, not moving, and just gradually speeding up. Now the gray line is a little bit different. Here we sort of have both types of motion. Initially, the object remains at just a single position, so it's not moving at all. Its velocity is 0. And then it makes a change so that at the later portions of its motion, it is a straight line. It is constant speed. And so our graph will have to indicate a horizontal line at 0 velocity and then a horizontal line at the new velocity. And because D slopes downward, we need to indicate a negative velocity. Now there is one more piece of information that we can get from a velocity versus time graph, and that is displacement or distance, how far the object goes. It's a little bit more complex. There's a separate video for that. Take a look for that on the website.